So welcome everyone to the 5th session in this semester of the Vacuum Transport Seminar. And today we have two very interesting talks, which Daniel will introduce to you in a second. But before, I want to point out that you can all ask the questions in the Q&A button in the Zoom. So this should be right next to the chat. So you can click on that button and you can also ask your questions anonymously. So then after every talk, we can have a little discussion round and yeah, hopefully answer all of your questions. So without further ado, I would say we start with the first talk and I would give the word to Daniel.
Thanks, Andrea, and welcome everyone. Welcome to the 5th session of the Vacuum Transport Seminars. Today, as a first guest, we have the pleasure to welcome Shadi Shatter from Hyperloop Tunneling, who will be presenting us a bit more about their design of a tunnel boring machine with continuous lining extrusion. Maybe as you heard last year, Hyperloop Tunneling was again able to bring home the Innovation Award from the boring competition of Elon Musk. So we are quite thrilled to listen in to more of these insights. So without further ado, Shadi, I will leave the floor to you. Thank you very much for joining, and you can present your screen.
Thank you, Daniel. So yeah, thank you for the introduction and for the opportunity. I'm very happy to present you today some of the challenges behind the development of our tunnel boring machine with our novel continuous lining extrusion. So quickly about Hyperloop Tunneling. It was founded 3 years ago, and it was started, let's say, with the belief that to scale the Hyperloop concept over long distances, new tunneling technologies are probably needed. But our concept can also be used in traditional tunneling applications. We took part twice at the Auto Boring competition, and yeah, we're a mix of bachelor and master students from different universities, but we are mainly based in Zurich. So yeah, of our team, two quick pictures. The top left is us at our testing site in Dübendorf, close to Zurich. And the bottom right was from a few months back in Texas at the competition. A few insights from the competition took place at the end of March in Bastrop, Texas, close to the boring company headquarters. And yeah, it was a very nice experience, and we were able to get again the Innovation Award as well as the second place. It was the team with the fully assembled tunnel boring machine right before moving it to the digging site. And here the whole team with the machine. So for the technology, microtunneling, let's say the state of the art is what is often called the pipe jacking method. There is a nice overview on the right. So you start with some sort of pit, and then you have here inside a machine, a jacking station, which inserts the lining pipes. So the shield is basically what erodes and drills the tunnel. Then you insert those lining pipes inside and you push them inside the tunnel to basically build this tunnel structure. So the time is really limited. So the bottleneck is really this insertion of those lining pipes, this pipe jacking method. The other disadvantage is that you have no possibility to turn since you're inserting those straight sections. Talking about microtunneling, the standard is usually meant from between a diameters of 0.5 to around 2.8 meters. Sometimes can go up to 4 meters, but that's the standard what we mean when we say microtunneling. So let's look instead at what we designed. So these are tunnel boring machine, Groundhog Beta. It has a length of slightly more than 8 meters and a bit more than 3 tons of weight, for a diameter of slightly more than half a meter. And yes, looking at the components from left to right, we have the erosion, which is the removal of the soil, which is then mixed with a foam or conditioned with a foam. Then we have the steering, which aligns the erosion relative to the machine and allows to turn. Then the tunnel lining section, which was also the reason for the innovation award. We melt the polymer in this white rod, which is on a commercial extruder, and the polymer is then extruded to the outer wall of the machine, such that a tunnel is created. The Venturi section is responsible to basically suck the soil that was conditioned from the erosion and then to bring it back outside of the tunnel. And finally, we have the propulsion system. So it's basically clamps against the tunnel wall and then pushes the machine forward. And we have two set of plates in order to have a continuous advancement. So for the erosion, you have this cutter head with stone crushers, and yes, the cutter head basically rotates with thanks to a hydraulic motor. Then we have the steering, so a steward platform with 6 hydraulic cylinders, 6 degrees of freedom, and it also has the possibility of a jackhammer mode. Then the liner, so this extrusion lining system, we first heat a polymer and then we cool it down, and we feed the polymer granulate through a pneumatic system. But more details about the liner afterwards. So yeah, for the propulsion, as I said, 2 gripper plates, 100 kilonewton each, so up to 200 kilonewton in total. Continuous movement, and we developed several kind of controllers. We have just simple open loop controllers up to more advanced model predictive controllers. Then the starting platform where the machine is placed, which it's a simple structure. We can vary the starting angle depending on the type of tunnel that we want to dig. For the controlling software, we designed our own control system. We have custom-made PCBs with really many sensors. We have a custom user interface and with obviously a lot of safety features for manual override, automatic shutdown, and so on. And then also important is the power supply, let's say the high voltage power supply to the different components that we have. So more in details about the liner. We said we have this extruder inside. The polymer is in granulate form and first is sent through the pneumatic conveying system in this small box on top of the extruder. The polymer is heated up, extruded, and builds the shape that we want, the tunnel, let's say. The important feature is that over almost the entire length, which also goes through the Venturi section, we have a cooling system. So we have an annulus pipe that cools down the extruded polymer. What is an extruder? So extruder is essentially, it starts with some kind of hopper or a box where you put pellets or granulates. Then you need a motor that turns a screw, and with the friction and also with some additional heaters, the polymer is then melted. And at the end, you have some sort of nozzle to essentially extrude the polymer. Same principle as a normal 3D printer, but it's in a much bigger scale. Here I have just a simple video. It's not from our system, but we see the granulates in that kind of large hopper. And then here we have a large extruder, which is heated. The screw is turned, and then you get the material coming out. I chose this video because you really see the material, how it comes out. In this video, they then cool down the material. This is just industrial production of plastic pipes. In this video, they cool it down with water jet. In our case, we just use our tunnel, our entire, let's say, steel structure to cool it down using water. So moving on to the design challenges. The first one was really the polymer selection. Then the conveying of this polymer, so from the outside of the tunnel up to the extruder, and then the polymer cooling. Starting with the polymer selection, the first part is the mechanical properties. Clearly, the strength of the polymer affects the thickness, hence the mass of material of polymer required, and that's the main dimensioning factor for the extruder. And then also keeping in mind the relation with temperature of that material to really make sure that once the liner reaches the back of the machine, it's already really solid and well below the glass temperature. From the thermal point of view, the heat conductivity of the polymer affects a lot the cooling length. I also have a plot afterwards. Then the heat capacity clearly affects the heating power, so how much heat you need to give, both in terms of extruder and in terms of heating elements. Just to give you an idea, here it's a plot that we generated with our model for the cooling of the polymer. This takes into account the polymer, which starts in liquid form and then is brought down to the solid, up to solid, and then up to the structural temperature. And you can really see that the heat conduction of the polymer as a property can really have a big effect on the surface that you need to really cool it down. So this total tube length is meant the length of the cooling section that you need to bring it down from the extrusion temperature, so more than 200 degrees, down to the structural. And most of the polymers, they had a pretty bad heat conductivity. So most of the polymer, they really move in this area, which means if you don't find the right polymer, you're looking at a very long length to cool it down. And then the extrusion, the last parameter, because the viscosity of the polymer has a big effect on the extrusion power that you need, and then also the shrinkage. That's a very big problem, because if you're extruding and it shrinks, it will basically clamp on the surface and not move anymore. So in the end, it's essentially the selection of the base material and a filler, but there isn't really a perfect polymer. It's really a trade-off of different properties. And I would say the polymer, they have a lot of like these empirical relations and so on, which makes the estimation of some of these parameters even more complex. So yeah, I'm not gonna, let's say, give the exact composition of the polymer. That's also something that, for example, the boarding company was quite interested, but we worked a lot, and I can say that it's a lot of trial and error, and it's essentially a trade-off of this base material and some fillers. For the polymer conveying, this polymer in pellet form, the distance between the storage silo and the tunnel boring machine varies, and the extruder inlet has to be always full, like this hopper. And the first option that we looked at was a conveyor belt, but it's a simple solution, but it takes up too much space. That's why we looked at pneumatic conveying. There are different types. You can basically convey something in dilute phase where the pellets really fly in the air, or in a dense phase where you push it with higher pressure, but in kind of like waves. And then you can also do it with a pressure system or a vacuum system, depending if you push it from the outside or if you essentially suck the air from the other end. And yes, this is the system that we designed for the pneumatic conveying. At the top, there will be the connection to the silo. Here I have a short video. The quality is not so good, and you probably also can't hear much, but here's the polymer field from the top. This was just scaling of the scale. This would be the final hopper. This was just a simple code, which we start a series of valves open. We fill a certain quantity here inside, and then we start the conveying. Here, just see the tubes where there are particles flying really at around 70 kilometers per hour, which then go inside the hopper that we saw, which then looks something like this. So here it was like an overfill test, but we basically pushed the polymer inside this small box, and we tested this system quite a lot. And it worked relatively reliably. Final main challenge, the polymer cooling. So I already mentioned it a few times earlier, but really we want to bring down the polymer from the extrusion temperature down to the structural temperature. Modeling the cooling down is quite complex because you have empirical heat transfer modes. You have risk of coolant boiling because if you use water, and at the start you have your polymer at 200 degrees, then the average of the two temperatures, meaning the wall temperature, could be very close to 100 degrees. And then also the pressure drop in cooling section. In our case, we just basically connected our system to a water chiller, which basically has a closed loop, brings the cold water to the system, and then the hotter water back, and it's cooled down. This is, let's say, maybe to connect to this challenge. I would say if you really wanted to look at the perfect cooling system, cooling design would be to have some kind of channels with large surface area, highly conductive material, turbulent regime to enhance the heat transfer. Here you can imagine that it's not so different from our system. We would just have the polymer here on top. And this would be the perfect system, but it's obviously very expensive to manufacture. And you also have high cooling pressure losses. But these are, let's say, at least the thing to keep in mind. So the surface area and the turbulent regime are the most important things. Good. That was it for the technical part. Moving to the lessons learned. I would say to keep the design as simple as possible and use proven industrial concepts, meaning that you can still design a novel system, but still, let's say, count on some industrial concept. For example, the pneumatic conveying is used a lot in industry. They just use it on static pipes. Usually they can do them out of metal. In our case, we had to change that a bit. But essentially always go back to like industrial proven concept. I think that's a good philosophy. Test electronics and software thoroughly, especially when the teams are separated. In our case, we have the tunnel lining team, we have software team, electrical team. So it's yeah, it's always difficult to coordinate, especially people with maybe a different background, mechanical rather than electrical engineers. And I would say, yeah, there is a solution to almost every engineering problem. That's philosophy when, especially student projects, you see that you get to the point where you say, yeah, we're never going to make it, but in the end, most of the time, somehow you can find a solution. So yes, that was it from my side. Thank you for the attention. I see already something for the Q&A.
For the presentation, Shady. And so I will ask you the questions and you can choose answer them. So I saw some questions were more technical. There were some questions about the cooling part. One of them was, why are you not using an active cooling system? I think in the beginning you showed that you basically work with the soil around it, and but you also showed a bit with the water.
Yes,
there are some problems. Is there? Did you look into maybe different solutions for cooling?
Yes, so I would say for example, during simulation, one would say that part of the heat for the polymer is taken by the soil and part is taken by your active system if you want to have one. In our case, I would say that it was just really a matter of looking at the kind of heat that we were talking about. In our case, we were talking like several kilowatts. So when you have this kind of like heat load, in our case, it was kind of natural to look at some kind of like liquid air cooling. So that was the main driving factor. In the end, I would say how it's actually, let's say part of the challenge is also the small space, because you have to imagine this half a meter with an extruder that gives a lot of heat. There are a lot of challenges in terms of all the heat that basically goes everywhere to electronics, sensors, really everything. So in our case, going for an active cooling was the only reasonable option to really have a system that can like continue to operate for hours. Yes.
Yeah, there was also one question. Did you also compare or take into account the temperature of the soils, and this can also differ in different regions?
Yeah, so about that, I would say that because of the difficulty in modeling everything, the philosophy was always let's try to be as conservative as possible, meaning because the soil can vary a lot if we test in Switzerland, if it rained or not recently. So let's say Switzerland rather than the desert in Texas. So this large difference made us, let's say, be a bit conservative, meaning we take maybe the worst case assumption, like almost no soil heat pickup, and we say all the heat has to be taken by our system. I think that's let's say the philosophy that we had most of the time.
Okay, yeah. And I see there were also a few questions like related to Hyperloop. Do you think your boring technique is also an option for Hyperloop in the future?
Yeah, so I would say that, let's say now we are still in the at the level of like a prototype. We tested it, but we still need to further develop our system. And but I say in the long run, this kind of continuous drilling technique can really, let's say, can really bring a lot compared to current design. And I don't want to talk about like completely revolutionize the industry, because these are this is what we say, let's say, in our presentation, but it's difficult to predict how everything will turn out. But I think this kind of like continuous digging system can really have can really bring a lot of improvements in the way that tunnels can be digged much more quickly and with also cheaper cost and so on. So I would say I'm confident that it's a very interesting concept.
Okay, nice. And maybe more about your team. Like now you've had the pleasure to win the second place again. Do you already know what kind of changes you will be doing on your machine? Can you maybe like give us some ideas what you're gonna improve for the next season?
Well, I would say the most important thing is that it's really like testing more and to really prove the reliability in different conditions, and only once you reach a certain level of reliability, because this is really the main goal for us in the near future. Once you've been able to test it a lot and show the reliability, then you can think about more, let's say, specific design changes. But I would say yes, that at least the reliability and more testing time is our focus for the near future.
Okay, nice. And maybe one last question. I saw, are you the first team to use polymer concrete, or?
So other teams, they used some polymer pipes, just some, I think, HDP pipes or some kind, just pre-made, let's say, but they still use this kind of like pipe checking method, essentially pushing those pipes inside. At least at the competition, and as far as I know, overall, it's we're probably the first one to try to design this extrusion system that can really allow to have this continuous movement and also turns and so on.
Okay, nice. So you were the first team with the extrusion part.
Yes.
Okay, nice. Congrats on that.
Thank you.
Okay, so I'd say then we can continue with the second talk. Thanks again, Shady, for your presentation and for answering all of the questions.
Thank you very much for the opportunity.
And then I would give the word to Daniel again to present the second talk.
Thank you very much, Shady, for the nice presentation. Now we have our second talk, which is tackling the challenge of the infrastructure, more especially how to realize infrastructure when looking at composite materials such as concrete. For this talk, we have the pleasure to welcome today Karkit Kulkarni from Quintrans Hyperloop, who is co-founder and chief operations officer from this team, as well as Prasanna Kadambi, who is a CTO and colleague from Karkit, who exactly will give us a deeper detail on how they are approaching this big challenge when looking at composite materials. Very much looking forward to the talk, and especially in getting more insights. Since here at EuroTube, we're also relying on concrete as a prime material for the infrastructure.
Yeah, thanks a lot. Thanks a lot, Daniel.
Hello, Daniel. Thank you so much for the introduction. Due to some technical issues, I won't be able to present right now at the moment, but Kadam will take on.
Yeah, thank you, Karthik. Thanks a lot for taking this. First of all, thanks a lot for providing this opportunity today, and I will quickly jump on to the presentation maybe. So yeah, so we as Karthik said, we are Quintrans Hyperloop. We are a startup based out of Pune, Maharashtra, India. We are currently developing infrastructure solutions for implementing Hyperloop as a mode of transport. We are looking into multiple infrastructure challenges, be the tube, the pipe itself, then the track itself that will be laid inside it, and along with that, the vehicle that will be maneuvering over this track inside a vacuum kind of a chamber. So I'll just quickly take you through the agenda of the presentation. So I'll just talk about briefly what is the technology here at Quintrans that we are trying to develop. Concrete tubes. So why exactly, we shifted our entire ideology towards, developing a whole new material in order to sustain vacuum, and how exactly does concrete helps us in achieving the kind of performance that we are expecting from this mode of transport, and what are the ways through which, are we are going to traverse this entire, development of the technology, right from a prototype scale to a commercial level technology being deployed. Will I also talk about brief in terms of the process methodology. So what is exactly, the process mindset that we have set over here in order to achieve commercial product here at Quintrons, and not just with respect to exactly the concrete pipe. It applies fundamentally to all the technologies that we are trying to work over here. Little and here and there can be changes, but this methodology helps us in faster scaling, helps us in getting ground up technology, and thereon we can make amendments in terms of reaching better performance parameters, making changes to by tweaking different parameters itself. So, and at the end, I will talk about in terms of what are the test results that we have observed so far in terms of the prototype that we have developed, and I'll just talk about in terms of the lessons learned and what we can likely see ahead in terms of going ahead with this technology. So this is a very fundamental representation of in terms of what exactly are the three major components of the technology here at Quintrons. So like I said, we are focusing on the large tubular sections that will be laid on the pylon structures, or maybe on the ground structures, or maybe underground as well, as a matter of fact. And I'll come to the point why exactly our solution aligns very effectively in terms of developing an underground infrastructure as well. Apart from that, we are also looking at an electromagnetic track, which essentially consists of conductors which will be installed all around the track, and it will also consist of the propulsion mechanism as well, which will be laid down on the track itself. Then at the end, the vehicle itself is a very important component and the piece of infrastructure. The vehicle will be designed depending upon the dynamic requirements as we receive, be it for cargo, be it for passenger, and maybe I can talk maybe more upon in terms of if there are questions at the end with regards to the vehicle. So yeah, so why we jumped onto something concrete? We essentially realized that concrete has been for a large amount of time in the industry has been utilized in many sewerage applications, or maybe these pipes have been utilized for doing the underground lining for be it the railways, or be it the railway system, be it the metro system, and with a completely different kind of a challenge that Hyperloop poses, in that having a vacuum pressure environment sustained inside this tube structure presents a lot of design challenges, and especially gives a lot of scope of innovation into this product being developed at a commercial level. So why we had so much inclination towards concrete as as an inherent material for the tubes is the number one reason lies in the cost effectiveness. So fundamentally, Hyperloop has been facing a lot of backlash in terms of the infrastructural costs that are incurred at the initial level. So in order to decrease those infrastructure costs and tackle the first set of problems, it would be essential that we are able to develop a structure that is cost effective and at the same time is able to provide the same amount of performance as compared to what stainless steel counterparts, or maybe the other kind of composite steels that other companies are trying to utilize and set up a commercial tube line. Second is the sustainable process that is behind this. So essentially there is a very fundamental study in terms of if ever you produce 1 kg of steel inside, or if ever the production of a 1 kg of steel utilizes X amount of carbon emissions being released. So certainly if you look at concrete as a material part, there are certainly less amount of carbon emissions that are being released with the usage of such kind of materials. And the second part the third very most interesting part that we looked at around is concrete itself can be manufactured in situ with respect to where the infrastructure is being developed. At a higher scale, when we look at commercialization of the entire Hyperloop technology, there will be very large scale tubes, maybe of the diameter of 4 meters, 5 meters. People are still debating about it. If ever carrying these large scale tubes, large scale length diameter tubes would require very heavy transport infrastructure from one point to the another, and this itself will cost huge money in terms of transportation of these kind of products. Whereas Hyperloop, whereas concrete tubes offer in situ manufacturing flexibility. So essentially, wherever the infrastructure is being developed, we can have the entire in situ manufacturing facility right beside the infrastructure being developed, and we can produce those tubes over there and then on to maybe assemble those tubes along the same corridor itself. So it essentially saves cost, a lot of the transport, and also since there will be a fundamental amount of row that will be acquired in order to develop the technology, so the row can be essentially utilized at the same time while the manufacturing and the assembling is going on. The last point is actually in terms of, if you look at the performance parameters that you have set for having the vacuum pressure inside, or what kind of structural strength it has to regain, for the longevity of the entire product, what is the durability cycles that we are looking onto. It provides concrete tubes itself has a very optimum cost to performance ratio, and while fixing the performance and looking at the different cost aspects of different structures based out of steel, composite steels, or maybe concrete as well, we realize that concrete gives us a better opportunity in order to go ahead with. So how did we essentially start with building the entire concept around it? So we started with the initial material lab trials with respect to the existing material compositions that we have commercially. We built smaller scale concrete tubular structures based out of pure concrete, and then we tested them. We tested each and every sample with respect to performance parameters that we had set in the beginning, and we realized that we had to come up with a certain objective while we are going for a larger scale tube. So we decided that it should be a simple structure and with an optimum composition, whereas high strength and low porosity would be the third most important parameter, and the last parameter would be in terms of the real-time testing that needs to be done for the entire concrete tube. So since these tubes will be subjected to multiple environment conditions throughout the day, throughout the night, so it's important that we understand how these tubes are going to react to it, rather than having them in a completely isolated lab scale environment where we are controlling essentially the entire environment parameter. So yeah, so looking at the process methodology, like I said, what exactly is the process methodology over here? We are looking at more towards an experimental approach driven by quantified changes in results. So look, if ever we keep on iterating the design continuously one and again, it is very hard for, especially for developing design structures out of concrete and to arrive at a product, rather than working ground up, coming with a technology and then trying to develop something out of this entire piece. We are focusing more towards process-based methodology, rather than wherein we have experimental approach, where we are quantifying at each and every stage what are the changes that we are doing and what the results that we are trying to optimize. So we looked at, like I said, the different material options and the structure options that are in the current manufacturing, which suits to the current manufacturing technology that is available here in India. And with respect to that itself, the requirements that we received from them, we designed the entire material anatomy around it. So the entire process, it's actually a very rigorous iterative process, wherein at each and every stage we are trying to optimize each and every composition and then arrive to a particular optimum solution in terms of the average compressive strength, the penetration depth of the concrete, how much amount of porosity it can hold, and something like that. So we had a more focus on implementation first and getting the first prototype on ground, and then test on on to, using multiple parameters and then keep on optimizing in order to build a commercial, prototype. So for the larger scale diameter tubes, we will be relying on the current test data results that we obtain, and using that itself we'll be able to better justify the reliability of the entire structure, and at the same time we can, utilize it directly for a commercial application that we can look forward to. So the entire chain of events starts from, the knowing the existing, what are the material compositions that are available, and then a controlled addition of different admixtures, and to observe the results at the end of, doing the test results at lab scale. Further on to, if ever we are able to have the optimum test results from the lab, and then developing a pure, tubular structure of the pure modified concrete, and then modifying the concrete in terms of, looking at the manufacturability that we have. So when we, design material compositions at lab scale level, it is very important to integrate it with what manufacturing setups that we have, and rather than, keep on going completely unaware about how the manufacturing machines can actually suit those material compositions. So we took both of those ends at two parts of the company, and we tried to integrate it at this point. And the entire composition that we arrived at the late, we optimized it in a usage for a reinforced concrete composite design structure, and then on to we developed the entire tube structure out of it. So these are the fundamental design considerations that we took into picture. So as I said that we try to optimize at first at what are the conditions onto which the when a vacuum load is subjected onto the entire tube, what are the forces that can act on it. And more so, along with the forces, there can be environmental parameters which I'll later come on to, which actually have a significant amount of you can say effect on what is the vacuum depressurization rate and the pressurization rate. So we set up that an ample temperature and ambient temperature and pressure conditions of 25 degrees Celsius and 760 mmHg. What are the kind of pressures that forces that can be acting on the tube? So essentially there are three fundamental loads that we qualified that will be acting on the tube, as in when it is subjected to extra vacuum loads without any external loads that are acting on the tube. So the first component is the longitudinal load that is actually acting on the tube along the axial direction of it, and the radial direction is essentially the forces acting on the walls towards the inside part of the tube. And then there is the dead weight itself, or the entire tube, that is acting on the downward side, whether it is supported from a single pylon structure, it is supported from a double pylon structure. That will vary a bit in terms of what kind of strength do we need in order to resist the you can say dimensional changes because of this dead weight structure. But as we realize that the radial component is something that is very significant and is more subjected to cause the failure of the tube or rupture of the tube rather than the longitudinal and the dead weight. So we designed the entire tube anatomy based on considering what are the radial loads and the radial stresses that are acting on the tube. So in terms of getting the material results that we observed from the lab scale prototypes that we had formed, an average compressive strength of the material that we observed was around 75 megapascals or 76 megapascals using accelerated curing method. This is a 14-day period strength that we have observed over here, with a average penetration depth of around 1.26 mm, which has been significantly reduced as compared to what ultra high performance concrete compositions that we are readily available in the market and are currently being utilized. So we latched on to using those design considerations to particular tube specification. So in order to, if I talk about more in terms of the material, what exactly is the specification of the tube, so we can observe that the current composition that we are utilizing, its density can vary from 2600 to 2900 kg per meter cube, depending upon a slight change in the admixtures of the entire composition, in terms of the sand, in terms of the entire cement that is being added, and the aggregate as well. the grade of the material, essentially we started from a M60 kind of, readily available material and modified onto in order to gain these kind of compressive strength parameters, and also in order to arrive at a optimized solution wherein it has the better strength in terms of its tensile capabilities, as well as the compressive loads which are inherently acting because of the vacuum load on the tube. So these are some kind of parameters that we observed in terms of while we develop the entire material composition of the utilized you can say admixtures as well as the other components. The significant compositional changes that we looked onto as compared to what the current options are available in the market. I cannot really talk about what is the amount of weight by weight percentage or weight by volume percentage for these kind of compositions, but I can certainly tell you that sorry. So I can certainly tell you that these are some of the significant compositional changes that we have done. We have utilized a high performance water reducing agent fundamentally in order to lessen the entire porosity of the tube, and also to increase the compressive strength. There is a specialized admixture devised right from scratch in lab itself in order to both look at towards the fundamentally to reduce the porosity of the structure, and this along with that nano silica and micro silica are some of the important components that we have added onto the tube in order to arrive at these kind of compressive strength parameters that you can see it over on the left side of the screen. On the right side, this is a kind of like evolved model of the jacketed tube that currently we utilize in the underground structures in order to develop the entire tube lining. So we essentially there is a tube structure with a collar end on one side, and on the other side there is essentially we have attached a flange structure that we essentially can utilize for multiple applications. One is essentially the flange can be utilized both in case of an underground structure in order to push the tube inside, and the flange structure essentially can be utilized on an elevated corridor as well in terms of having an expansion kind of a joint, or just welding two tubes together with having same kind of flange joints on one end of the tube. So what we realized was the two ends of the tubes are something which can be interchanged at given point of time. So basically they can be utilized in any sort of pair possible. It can be a collar pair, it can be a collar flange pair, it can be a flange pair. So that is the kind of you can say in terms of structural you can say challenge that we are trying to solve over here. But it is essentially realizing from the existing tube structures that we have, and basically optimizing it with the kind of transport model that we are trying to develop over here. And the tube that we recently developed and we are currently testing it, is currently of the ID of 1.2 meters in diameter and with an OD of 1.45 meters in outer diameter. It also for most of the for most of the vacuum connections that we see on concrete based tubes, we are significantly observing that there are multiple researchers working out of Korea. There's also some very great research going on in Europe as well. The most fundamental thing that we are also working on is a vacuum connection holes on walls as well. And because of this, what kind of stress concentration can act on the walls? Because there is a huge amount of pressure change or pressure difference that is acting along the two ends of this small diameter you can say a passage itself. And in order to foresee what kind of stress challenges can act on the nodes on the walls of the tube is something that we are looking at in terms of research capabilities here at Quintrans. So we focused that we needed to have vacuum connection or holes on the walls of the tube. And with this itself, we will also look at, what are the challenges that we can solve once we have larger diameter holes on the walls as well. In terms of talking about, once developing the entire tube and once starting with the testing characteristics, there are two fundamental things that we observed, at the very end in the conclusion of the entire, testing phase that is currently going on as of now. That is the depressurization characteristics vary, even though slightly, but they do vary with the surrounding environmental air parameters, the ambient temperature, the relative humidity, what is the atmospheric, pressure at the location. Even though the, variance is not that too much. So if you look at, the down to characteristics which are mentioned over here. So one of the testing conditions is probably during the daytime. It's more during the afternoon hours where the relative humidity is much lesser because of the higher temperature of the air, and the atmospheric pressure is also kind of low at that point of time. So if you see the testing depressurization time that it takes from 0 to coming on to a maximum vacuum pressure inside the tube of around 715 mmHg, which is slightly like 94.5% vacuum that is being held inside the tube. So while going traversing along this curve, if you look at the kind of, the slope for this curve, and you look at the slope of this curve, so you see that there is not that kind of a steep part wherein, this curve is evolving, or the depressurization curve is evolving. Whereas in this case, there is a very high steep curve. If you look at, somewhere a time during, the evening part, wherein the relative humidity is more, the temperature of the air has lessened as well significantly, and the atmospheric pressure doesn't really change much, but there is definitely a change. So this is the kind of, observance that we are trying to, have over at here at, in terms of data capabilities, so that we can analyze and try to have, something of a material structure which will, not necessarily be independent, but at the same time would not be much influenced by these kind of testing conditions. The pressurization time, once the entire, vacuum pressure has been reached up to this point, it normally takes for at any part of the day, it takes normally around 50 to 54 hours in order to pressurize the entire tube to, equal pressure on both sides, be it on the inside, on the outside. And this is something which is not very, varying with the time or with any of the parameters. It is very consistent between 50 to 54 hours. So in terms of the testing, one more points that we observed was, so having, a setup of these kind of data parameters is something that might not be very significant at this early stage, but given the fact that vacuum created inside a concrete structure is something that is not very standardized, or there's not much data available in terms of, having a reference onto. But this is something that, we want to build right from scratch, so that we have better capabilities on the, next segment of, the development here, so that we can, better leverage this data in order to have a more optimized structure. So in terms of looking at, the conclusion, what are the lessons that we have learned so far in terms of the testing going on and also the manufacturing, we want to understand, the entire structural changes or the testing changes, result changes that might occur with, a kind of a homogeneous structure or a hybrid structure that we have. So we are looking more towards capability of developing an entire concrete tube with, maybe no reinforcement bar or less reinforcement bars and more concrete. So something that we are also trying to explore. Apart from that, we are also trying to have, sensors mounted on the entire wall part of the tube, and understand what are, the dimensional changes that are occurring. Even though they might not be very significant, the dimensions might not change a lot, the, the concrete tubes might not expand or shrink in a very short amount of time, but we want to get those data in terms of, while we are doing the depressurization and the pressurization. And this data will, be significant in a very longer run, not in a very shorter run of time. The most interesting part which we actually are looking towards is this entire tube model is something that will help us to leverage the scope of artificial intelligence and data analytics in order to study material strength patterns with varying composition parameters. So all of the testing, lab testing that we have done so far, all of the compositional changes at each and every iteration step that we have observed, we can feed it onto an artificial intelligence kind of a model in order to get an optimized model with somewhat reliable accuracy, in order to understand that if ever we are changing multiple compositions at the same time and not controlled composition changing, what kind of strength parameters can we predict in terms of once the testing is done or once the lab samples are casted. So that is very something interesting that we are trying to develop or explore here at Quintrans. So this will help us in the future runs in order to develop tubes in a much faster way, and at the same time we can adhere it to what are the changing patterns in the manufacturing technology as well. Innovation in manufacturing method of mixing the material is also something that we are looking towards, and the next part is the casting process as well, in order to improve the porosity of the finished structure. Currently all of the testing setups in order to develop concrete tubes are mainly because of vibration casting, or maybe there are people who are also using spin casting as a method. But we want to explore into different manufacturing methods as well, so looking at in terms of what are the 3D printing capabilities as well, in terms of the additive manufacturing. So those are the changes in the manufacturing method as well, if we want to explore, in order to see how it essentially affects the entire structure of the material. So all in all, what we think is that gathering more and more data with respect to concrete as a a material for having vacuum inside it is very important at this point of time, rather than trying to build more and more innovation into it, because once more and more data is into place, we can standardize the structure better and work towards a better innovation kind of a model. And that is something, the kind of approach that we are trying to follow, and hopefully it will reveal some good results for us in terms of the long-term vision that we see for developing commercial structures out of it. So yeah, thanks a lot for patiently listening to me, and I'll be happy to take on the questions as we speak. Yeah.
Yeah, thanks, Prasanna, for the talk. I see there are also a lot of questions, so we will just enter straight into them. The first question from the audience, someone is asking, how does the testing tube look like?
Okay. So if you can see at the background of this, so this is basically the tube itself, which is that we have developed. Maybe this will be better for you, I don't know.
Yeah, no.
So yeah, so this is the tube structure that we have built. Yeah, so this is essentially the collar lining that we have on one part of the tube, and there's a flange lining on the back part of the tube, and we have welded an entire steel structured door in order to seal the entire structure and create a essentially a vacuum pressure inside the surrounding, and beat a complete leak proof kind of a structure. So, and we, like I said, there is a vacuum connection on the wall part of the tube, and this essentially we have a threaded structure which is inserted inside the tube in order to connect those vacuum joints. Yeah.
Mm-hmm. And when now looking at the diffusion through the concrete, have you implemented such a diffusion barrier? Do you have such a model which is able to also quantify the amount of air which is passing through the concrete? Let's say to better understand what is the, let's say, the effect of this phenomenon on concrete.
Right. So in terms of looking at how exactly that is actually a very interesting question. So we are working towards something of, and trying to predict a simulation model wherein we can essentially understand with the depressurization and the pressurization how much amount of air is being trapped into the porous parts of the tube. So once we are able to quantify that part, we'll be able to better understand what is the air that is essentially being drawn out, and what is the air that essentially stays inside, and because of that we are not able to go up to higher levels of vacuum, maybe say around 95 or 98%. So that is the barrier that we are trying to look towards. But essentially what we had a performance parameter that we set here at as a company. We wanted to achieve 90% as a goal that we wanted to have, because at that moment we have the better energy efficiency as well for the vacuum pumps that are operating, and at the same time we are also able to reduce the you can say air drag loads that are acting on the vehicle. But it surpassed to our expectations. It went up to 94%. So that was something that we didn't really expect. But now that we see that there are capabilities to go higher above this, so we will certainly like to look into that. Yeah.
So this means this is basically your first prototype you tested under vacuum. Have you ever conducted, let's say, small scale tests, material tests, where you only look at the concrete itself, let's say to decrease the risk when scaling up the test setup?
As we understand, for the smaller scale setups that we build and that we have tested out of pure concrete tubular structures, we understand that once scaled onto different levels, say 1:3 or 1:1, the testing parameters change a lot. So that is the kind of non-uniform results that we observed as compared to what we have seen it in steel. So when you scale in steel from lesser sizes to higher sizes, there is not much changes in terms of the results that we obtain, but in concrete there is certainly that. So it is very important for us to develop something at scale itself, and then trying to understand how exactly we can predict it for smaller scales or maybe for larger scales. Yeah.
Okay, and in this regard, do you only test the tubes under vacuum, or do you also perform, or are you envisioning to perform destructive tests or more cyclic fatigue tests to check really the properties and of concrete on the long run?
So for the fatigue testing is something that we are currently looking on to. There are not much lab setups across the country which actually work towards a fatigue testing of a concrete waste tube. So that is something that we are looking on to. Destructive testing for concrete tubes is something that we have done for smaller scale prototypes, and that is what we have been comparing it with results to the lab scale sample results that we have observed. So that is something that we have. Apart from that, the hydrostatic tests that are done for concrete tubes is something that we are also looked into, but fatigue testing is something that we are still looking forward. Yeah.
Okay. Yeah, I guess because it's also the last step to validate the design of the concrete tube.
Right.
So
right.
That's the last question from the audience. It's more now regarding the manufacturing of the pipe. When you refer to in situ manufacturing, what exactly do you mean with in situ, and how close is this manufacturing plant or in situ manufacturing from the actual Hyperloop line?
So if I give you a sense of that, so essentially there are large scale pylon girders that are also manufactured right beside whenever there is a metro structure that is being laid out. Similar to that, we can have something for concrete tubes as well that can be set up right beside where the entire elevated track can be built, or where the entire underground track is being built. So the main challenge that we solve is that these tubes will be of very large scale in diameters, and transporting them over large distances would be a very challenging task, because with that kind of transportation options that are available currently in the country, it is very insignificant in terms of putting that much amount of cost, and which will be incurred ultimately in the project itself. So in situ manufacturing is something that we can develop inside right at the site beside where the entire track is being laid, and this is something that we are trying to explore in terms of feasibility with the manufacturers itself, whether or not they are will be able to come the amount of time that they will require in order to set up their entire manufacturing setup over there, whether it is feasible with respect to what current models that we can follow. So far we observed that there is certainly a cost reduction in that kind of aspect, but there needs to be more understanding for various factors involved.
Yeah, currently, if I'm audible, I would like to add some points on that. So,
Yeah, sure.
Basically, with in-situ manufacturing, we are focusing mainly on where we are seeing track changing facilities. So wherever we are changing the tracks, there is not specific moves that can be developed. to manufacture the tube in certain way. So in situ manufacturing, we are trying to see the different kinds of molds that we can manufacture to use this in case of changing the lanes in Hyperloop system in a large scale.
That was not completely clear to understand. Prasanna, did you get the question? Just to summarize, because it was not completely understandable.
Yeah, so I guess maybe Karthik lost his voice in between. So essentially, as I understand, you know, the in situ manufacturing is just like what I explained, is it's essentially to reduce that cost component of the entire logistics of these large scale tubes, and you know, essentially realize how these tubes can be built right on site and can be assembled at the place itself. So that is where you can essentially, you know, leverage the concept of, you know, in situ.
Yeah, that makes a lot of sense. Then the last question is more now to showcase your technology. Are you planning to unveil a certain type of test track where eventually also vehicles can be tested?
Right. So we are currently working on a 100-meter test track here itself in Pune, Maharashtra. So it will be a completely contactless mode of you know, vehicle movement that will take place from point A to point B, wherein we are also for the first time demonstrating a lane change capability on the basis of a ground you know, propulsion topology. There has been a lane change that has been demonstrated by hard Hyperloop in terms of, you know, the upper topology track that they have, but this is something for the first time that we are trying to develop and see if ever we can, you know, build this into and integrate this into our tube structure as well. So yeah.
Okay, and when roughly are we? Will it be ready so such that we can pass by and visit it?
Yeah, so we are looking at timelines of around 2024 end. So we are currently into the groundwork phase as of now. So we are developing the foundation of the entire land. So hopefully we are able to, when we are able to do the entire setup over here, we'll be happy to have an unveil event, and we can hopefully have a, you know, session here as well.
Excellent. Then we wish you great luck, great success for that, and
Thank you.
I think also the question round is over. So with this said, I will then hand over it to you, Andrea.
Yes, thank you, Daniel. And thanks a lot for our two speakers today for the insight into their work. And also thanks a lot to all of you joining and for participating in the Q&A. And so this is already the second last edition of this semester, but we have one more to go. So next week on the 12th of June, we have our last edition of this semester, and we are going to have two interesting talks again. So the first one is going to be of two engineers from a student team, the mu0 Hyperloop, and they are going to present to us a study on drag savings and energy efficiency of the low pressure system in the Hyperloop transport with CFD simulations. And the second talk is going to be of Emanuele Salonico, and he will present to us a study on a demand-based approach to determine a possible European Hyperloop network. So thanks again to everyone, and I hope to see all of you next week, and I wish you a nice evening. Thank you and goodbye.